This is Michael Altos recording Uptake and Distribution of Inhalational Anesthetics, Part 2. It's time for us to discuss induction. Induction is the process of getting agent from the anesthesia machine into the patient's brain so they go to sleep. And we're going to start by considering a very simple setup, just an anesthesia machine and a breathing circuit with a little piece at the end. Our goal is to achieve a steady state of anesthetic partial pressures throughout this little system. So we have a machine which has a vaporizer, and it adds agent to the fresh gas flow at a fixed concentration, let's say 1% sevoflurane. And the fresh gas mixes with the circuit gas and the bag and the tubing and whatever else is in this circuit. And maybe it gets absorbed into the plastic a little bit. But eventually the system achieves equilibrium, and the concentration of agent in this circuit rises until it gets to our final concentration. So now let's add some lungs, because without lungs this is a pretty boring system. We turn on the sevoflurane and eventually it becomes 1% sevoflurane. Now we add some lungs, and now we're going to discuss some terms here. So we have Fi. Fi is the fractional concentration of agent leaving the circuit. It's the inspired concentration, Fi. And when this system up to this point right here is filled up with sevoflurane, Fi is, let's say, 1% sevoflurane, okay? Fa is your alveolar concentration. It's the fractional concentration of agent in the lungs. Initially, Fi is, let's say, 1% sevoflurane, but Fa is 0, because when we first connect this thing to the patient's lungs, there's no sevoflurane in their lungs, so Fa is 0. And if we look at this ratio of Fa to Fi, it's 0, because Fa is 0. Now these compartments will equilibrate over time, just as the system equilibrated above when there was no lungs attached to the system. And we can define this system as being at equilibrium when Fa and Fi are the same, or when the Fa to Fi ratio is 1. And a fast induction would mean that this ratio approaches 1 very quickly. And the reason we care about this, of course, is because Fa is proportional to Pa. Right? 1% sevoflurane is proportional to a certain partial pressure of sevoflurane. And in the long run, we know that at equilibrium, the partial pressure in the alveoli equals in the blood, which equals in the brain. So this is the system that we're setting up to consider. This is a curve that shows induction as a function of time. This is a very important curve that you need to know. Fa divided by Fa is a function of time. Every agent starts with an Fa over Fi of 0 at time 0, because at time 0 there is no agent in the lungs, in the alveoli. And then let's just start with sevoflurane. Over time, the concentration rises very rapidly, and then it starts to level off, and the system will be at equilibrium when this curve approaches 1, when the Fa to Fi ratio is 1. Different agents have different speeds of induction. So we see nitrous oxide has a very fast induction. Halothane has a very slow induction. You will notice that the most soluble agents are at the low end of the spectrum, and the most insoluble agents are at the top of the spectrum. And we're going to see why that is shortly. Take a moment to consider any questions that you might have, and then we're going to go on. Now, a system with just lungs isn't very interesting. We're going to add some pulmonary blood flow now, something to take agent away from the lungs. And it's going to become a little bit more interesting now. So we have agent passing from the lungs into the blood. And we have arterial blood that goes away from the lungs. We have venous blood that comes back towards the lungs. And how do we describe the movement of gas from the lungs to the blood? Well, that's our blood gas partition coefficient. soluble agents with a high partition coefficient very rapidly leave the lungs because they're soluble in blood. The non-soluble agents with a low partition coefficient leave the lungs slowly because they are not very soluble. So let's look at some examples. I just want to make this as practical and tangible as possible for you. The blood gas partition coefficient of nitrous oxide is 0.47. And we can think of this in different ways. We could think of this as meaning a milliliter of blood holds only 0.47 as much of nitrous oxide as a milliliter of air. About half as much nitrous oxide. Or we could say blood dissolves nitrous oxide only about half as well as air does. And we can do this for soluble things too, like halothane. Halothane has a coefficient of 2.4. We can say a milliliter of blood is 2.5 times more able to hold halothane than a milliliter of air. It can hold 2.5 times more. We can say blood dissolves halothane 2.5 times better than air can. So this is what the partition coefficient means, and it's describing now this interface between the air in the lungs and the blood in the pulmonary vasculature. This is called uptake. This arrow is uptake, agent going from the lungs to the blood. That is the definition of uptake. This is very important. Of course, our system doesn't end with a meaningless cycle of pulmonary vasculature. Our system has brain and muscles and fat that are all connected to that vasculature. And as the blood travels to different tissues, the agent passes from the blood into each tissue. And this movement is dictated by its own coefficient, the tissue blood partition coefficient of various tissues. And when the agent moves from the blood to the tissue, well, now the blood that returns back to the lungs is got like more room to absorb more agent from the lungs. And the process continues. And this will continue until the system reaches equilibrium. So let's review. We have our system primed and ready to go with an Fi of, let's say, 1% sevoflurane. We add lungs. The lungs start initially with an Fa of 0. There's nothing in the lungs. But over time, this system equilibrates until the lungs reach a 1% sevoflurane. Right? And Fa is equal to Fi. The Fa to Fi ratio is 1. But unfortunately, it doesn't end this simply because there's a vasculature with blood, and the blood is going to pick up gas from the lungs, and it's going to go into the blood as defined by some sort of a solubility coefficient. And this will continue until the P blood is equal to the P in the alveoli, and the system is at equilibrium. But again, the system is more complicated because the patient has lots of tissues, including a brain. And so finally, we have agent leaving the machine, going inspired into the patient, into their lungs, transferring from their lungs to their blood, and then from their blood to their brain. And at equilibrium, all three of these pressures are the same. So induction is putting the agent all the way into the brain so the patient goes to sleep. And we achieve this steady state of anesthetic concentration throughout the whole system. How fast does this happen? Well, the faster that Fi equals Fa, the faster that Fa builds up to equal the amount of concentration of gas we're putting in the system, the faster that happens, the faster induction is happening, the faster the patient goes to sleep. And you say, well, I don't care about the lungs, I care about the brain. But remember that every time I put something in the lungs, some of it goes to the blood and to the brain. And so every time I try to build up Fa, it leaks out and goes this way. And when Fa is finally able to build up, I'll know that, remember, partial pressures equilibrate. Fa is proportional to Pa. So when Pa has built up to a certain level, I know that it's the same in P blood, it's the same PCNS, and this is the process of induction. Uptake, which is this arrow, is just one step in induction. Uptake is just agent going from the lungs to the blood. And it's one step in induction, but it's actually, and here comes the part you're going to have to think about for a while. Uptake is sort of like the enemy of rapid induction, because the factors that make uptake fast cause Fa to drop. And we already said that we want Fa to rise rapidly. When Fa rises rapidly, it means Pa is rising rapidly. It means P blood is rising rapidly. It means PCNS is rising rapidly, and the patient's going to sleep quickly. But when there's fast uptake, FA doesn't rise rapidly because the uptake keeps going here. This is something we're going to have to think about for a while. I'll try to do some of it in this lecture, and then we'll talk about it in class. Uptake specifically, again, is moving anesthetic from the lung into the blood of the lung. Uptake is defined by three things that you must know: solubility, blood flow, and the gradient between the pressure of agent in the lungs and the pressure of agent in the blood. Solubility we've discussed. When an agent is very soluble, it is taken up rapidly because it would rather be dissolved in the blood, wouldn't it? So that's fast uptake. Q is alveolar blood flow, which is really the same as cardiac output in most normal people. And when you have a high cardiac output, you're continuously sending more and more blood. Think of it as more empty space to pick up agent from the lungs. So as alveolar blood flow, as cardiac output becomes higher, there's more uptake. And finally, and this I think is also pretty intuitive, the difference between the pressure gradient, the pressure of alveoli in the lungs and the pressure of alveoli in the blood. When that gradient is very high, we expect that agent will be driven from the lungs into the blood. But when the gradient is very low, when the pressures are very close to each other, we expect that there is not as much of a driving force for agent to move from the lungs into the blood. Once again, uptake is movement of agent from the lungs into the blood, and so uptake decreases FA, doesn't it? Because it's not building up in the lungs. The agent is moving out of the lungs. And uptake, the factors that increase uptake, therefore will slow induction. I'm sure you all have a lot of questions here. I very strongly encourage you to spend some time on this lecture. Look in the textbook. I personally think that Barish does a very nice job of describing this, maybe better than any of the other textbooks that I've looked at in detail. If you find a good source, feel free to share it with me or with the class. And then, of course, I'm happy to answer your questions. We said uptake is affected by solubility. That was one of the three factors that we just saw in the previous slide. And remember, I pointed out that induction seems to be pretty slow for the soluble agents and pretty rapid for the insoluble agents. And now if we look, we can start to understand why that's happening. Because when uptake is fast due to high solubility, then induction is slow. And so the most soluble agents have very fast uptake, but they also, as a result, are going to have very slow induction. I know many of you are thinking, look, if we don't have uptake, we don't have induction. So obviously we need uptake to have induction. How can it be that fast uptake means slow induction? And that's why I'm trying to be careful to say the factors that lead to fast uptake also lead to slow induction. And we're going to see what that means further. Remember that soluble anesthetics have a greater uptake, as we just saw, which means that the blood has a larger capacity for these drugs because the drugs are so soluble. It takes longer for the blood to become saturated with these drugs because they're so soluble. And it takes longer to reach equilibrium because they're so soluble. So for example, let's imagine halothane. A patient takes one deep breath of halothane. Now we know that the partition coefficient of halothane is about 2.5. It's 2.4. So it's 2.5 to 1. For every 2.5 parts in the blood, for every 2.5 parts in the blood, there's 1 part in the gas phase. So of these 3.5 parts, if we add them together, 2.5 out of 3.5 are in the blood, and 1 out of 3.5 are in the gas phase. So 2.5 out of 3.5 is about 71%. So in one breath of halothane, 71% of it moves into the blood, and only 28% of it stays in the lungs. That's due just to the partition coefficient. And we could calculate the FA/FI after one breath. Well, if 28% is in the lungs, So Fa over Fi is 0.286. And we can look at that. Right? 0.286 would be right about here for halothane. And I'm going to leave my pointer right there. Now let's imagine desflurane. So you inhale one breath of desflurane. And we know that desflurane has got a partition coefficient of 0.42, which means that only about 30%, 29% of the desflurane transfers to the blood. That's what, out of these 1 plus 0.42, out of these parts, 0.42 out of 1.42 goes to the blood. That's 29%. While the rest of it, 70%, stays in the lungs. And the Fa over Fi is 0.704. Let's go up here to desflurane, and we'll see we're right at about 0.7. So at the same time, look how much more desflurane has built up in the lungs. Why? Because it's not soluble in the blood. More than twice as much halothane compared to desflurane has to be transferred from the lungs to the blood before partial pressures equilibrate, and that's just after one breath. Then, of course, things will move into the blood and other places throughout the body, but we're just talking about that first breath. Let's look at this a different way. I found this in a textbook online, and I reproduced it for you here. This is just another way of thinking about things. Let's look at desflurane versus halothane. So in desflurane, we're pouring little molecules of desflurane into the lungs, and they go into the blood, and the blood becomes saturated very quickly. Desflurane is not very soluble. And then onto the brain. And the brain becomes saturated very quickly because desflurane is not very soluble. Compare that with halothane. In halothane, you pour tons of halothane in, and it goes into the blood, but the blood is like this infinite sink for halothane because halothane is so soluble. And think of how much halothane you have to pour into the system before you start to really build up levels of halothane. And so you can see how much more halothane you need before this system achieves some sort of equilibrium. I like this picture. I'm not saying it's a perfect analogy, but I think it helps understand that solubility is this idea that the compartment is very large when an agent is very soluble. We're going to stop here. This is obviously a challenging set of concepts. I know you can all understand it, but it takes some time. It took me some time, and that was with an extensive background in kinetics and pharmacology. So I expect that you won't all get this the first time, but please devote some effort to it, and we'll discuss it in class, and I'm happy to answer your questions.